take a moment to thank everyone for coming and joining the Energy Innovation Network on the subject matter of the emerging market of grid interactive efficient buildings, GEBs. My name is Kevin Osborne, and I'm a volunteer of EIN. Before we go into today's subject matter, I'd like to take a moment, about 5 minutes, to introduce you to EIN. So the Energy Innovation Network is foremost, it's a platform for bridging smart minds to help advance a more sustainable future. And with that, we started in 2015 in Silicon Valley. We are powered by volunteers from the United States, Europe, Asia, specifically like China and India and Africa. And we're having a growing focus on the high-tech industry and the energy industry. As of 2022, we have a wide presence of 5,000 industry professionals, experts, scholars, business elites that work in the energy, environment, and transportation industry, really to promote a platform of energy education, innovation, and overall to push towards a more sustainable future. So our reach is global. We have a significant amount here in the United States as we started in California. We have the presence in over 100 regions with those 5,000 plus members. We are a volunteer-based team. So we all have full-time jobs. To take me as an example, I work for a solar development firm called Synergy Power. Others are in academia or in the new energy fields like Tesla and transportation. Our team is very diversified. As you can see from some of these images, they come from different industries, different backgrounds. We have an advisory board of four key professionals that span both China and the US and are in the academia and policy and provide really important insight on new industry developments and positive suggestions. So you may ask, what do we do? At EIN, we are focused on three core pillars. The first one, as like today, we have events, informative topics that we host roughly about every month. We also have an education program for both students and professionals on different energy topics through a series. And third, we do an annual conference called the Inspire Summit. And it was launched back in 2019, and that is more of a multi-day conference where we bring in different businesses and presenters on a much larger scale compared to the smaller sized events. So we work with multiple different event partners. These are just some of the examples here. So I would be including global corporations, NGOs, and higher education institutes. I'd just like to give you a taste of some past events that we have done. So for example, we've talked about blockchain and how it can solve some of mass limitations. So in the transportation sector. Battery, so battery second life, obviously with the influx of new EVs, that comes a key question. This was from our conference at the Inspire Summit. It was on climate collaboration as one aspect, mobilizing finance into climate, adaptation, mitigation, and others have been around issues in Africa, such as water, energy, and food. And just a few more examples here: product management in the renewable energy sector, biofuel standards, and energy finance. So we cover a wide spectrum of subject matters and look to bring in experts in the fields. And we've had a lot of positive reviews from our members for the education program that we held. This is an example of a certificate that was earned, and just a lot of positive accolades there that we're very happy to support our community with. So we are active, and we have our website here at energyinnovation.network, and then join the Slack channel. I'll post these in the notes here in the chat box on the Zoom call. So if you want to access it, you're more than welcome to. And with that said, I want to come back to our key topic here today, the emerging market of grid interactive efficient buildings. So consider this fact here, that buildings today account for more than 70% of US electricity, 40% of all US energy, and at least 1/3 of the US economy-wide CO2 emissions, according to the US Department of Energy. That's a lot of demand on the power grid, and electrification in many segments will put more stress on the grid. With the advances in the digital age, business models and new distributed energy resources like wind and solar, buildings are at a point of evolving from a passive consumer, a one-way user of electricity, to active resources of the power grid. Think about smart buildings. This is the new era where buildings are moving towards managing cleaner energy resources and acting as flexible, energy efficient assets, working with the grid to balance loads, all the while still providing comfort occupants expect. To put this into measurable significance, the opportunity over the next 20 years, according to the Department of Energy, is $100 to $200 billion in the US electric power system cost savings. By reducing and shifting timing of electricity consumption, GEBs could decrease 6% of the total US power sector's CO2 emissions. So today, we are honored to have 3 distinguished guests to speak to you about GEBs from 3 vantage points. First, at an industry level. Second, a planning of a Department of Energy funded community demonstration project. And third, valuable insight from a design engineer. After the 3 presentations, we will have a 20-minute Q&A for the audience. So with no more further ado, I want to introduce our first speaker, Connor, who is an associate at Rocky Mountain Institute, carbon-free building practices. He helps share the vision for the grid interactive efficient buildings, GEBs, and formulates value propositions for grid and building owners alike. Connor authors papers on the carbon reduction potential and the technological implications of GEBs, performing analysis on a range of, for the DOE, NREL, CEC, and large private real estate holders. So with that, I'd like to turn this over to Connor.
Cool, thanks, Kevin. Well, I will share my screen here so I can start walking through some of my presentation. And kick off this event. So I appreciate the info. So I am going to be talking a little bit about the role of grid interactive efficient buildings, or GEBs, that they're going to play in the energy transition. So Kevin just gave a bit of an intro, but before I start rambling about my favorite topic, just to reiterate, my name is Connor Ussery. I'm an associate on RMI's Carbon-Free Buildings program. And like Kevin was saying before, I'm on a team that's focused specifically on grid interactive efficient buildings. So I have dug into the economics and the carbon impacts of GEBs, and I'll talk a little bit about that today. So RMI, just as a brief intro as well, was formerly known as Rocky Mountain Institute. We're an independent nonprofit that was founded about 40 years ago. We actually had our 40th birthday a couple weeks ago. And what we do is we work to transform the global energy systems through market-driven solutions that try to align with that 1.5 degrees that everybody hears about set by the IPCC. And we do that by engaging with businesses, policymakers, communities, other NGOs across the US and India, China, Southeast Asia, as well as Africa, to try and identify and scale energy system interventions that'll cut some of these greenhouse gas emissions. So very briefly, why are we even talking about buildings in the first place? Well, like Kevin said, buildings are the single largest emitter of greenhouse gases in the US. Our buildings consume 3/4 of our global electricity. They burn 1/3 of our natural gas, and in construction, including the demand for concrete and steel, is responsible for up to 1/5 of all of the industrial emissions. So in all, buildings are responsible for roughly 40% of our global greenhouse gas emissions. And anything we can do to try and cut that is going to be incredibly impactful. So the first piece that I'm going to dig into here is what even are good interactive efficient buildings. So a GEB, as we like to cut things into acronyms and talk about, are energy efficient buildings that optimize energy use for grid services, occupant needs and preferences, as well as cost reductions in a pretty continuous and integrated way. GEBs have a few primary features. They're efficient, which is that they're minimizing power draw from the electrical grid. They're smart. They have sensors and controls, which allow for buildings to optimize to owner preferences. They're connected, which allows for internal and external communications. And they're also flexible with the ability to manipulate their energy consumption and production. In order to avoid some of the worst impacts of climate change, our group at RMI has said that we need to cut our emissions in half by 2030, which is a pretty big goal. And GEBs play a pretty crucial part of that by shaping the way that we can reduce energy use and emissions in our buildings. So GEBs leverage 5 key strategies to adjust their building operations, to save money, to improve occupant comfort, and to become an asset on the utility grid. So those 5 key pieces are, they have to be efficient, which is the continuous reduction of energy consumption throughout the day without reducing occupant comfort. There's load shedding, which is the reduction of energy use for a short period of time. That strategy is often used and dispatched in response to demand response program calls, which I'll talk about a little bit later. There's load shifting, which is the shifting of energy consumption to different hours of the day to try and avoid high cost or high emissions times. That's also known as demand flexibility, which is how I will most likely be referring to it later. There's generation, which is the use of rooftop solar or other on-site resources to try and meet the demand of the building, and exporting any of that excess to the electricity grid. And then there's also modulation, which is the balancing of power supply and demand, or reactive power draw and supply. And that's done at a very short time scale. It's seconds or sub-seconds. So it should be noted that residential GEB buildings are not typically capable of doing this, but a commercial building might do that and has pretty strong effects on making sure that the grid is stable. So what actually makes a GEB a GEB? First of all, there's not a set checklist. There's not a governing body or something like that that says that you are or you're not. It's sort of just an ever evolving potential for buildings to be better. So a GEB can be commercial, it can be a residential building, it can be an industrial building. But a really great first step in order to becoming a GEB is really just long-standing efficiency improvements that have existed for a while, like better insulation, fenestration, and more efficient appliances. But the best of them are really just greater investment in hardware and software. So there are a lot of these GEB measures that are commercially available today and have been for a while. And this chart sort of shows that range from commercially available on the left to there's ones that are more in development on the right there, but they range from controls technologies to try and help monitor and control those HVAC and lighting to the actual mechanical and electrical systems with the ability to store some of that thermal and electrical energy for later uses in the day. So before I get into some of the actual implications of GEBs, I just want to talk a little bit about the technical aspects of how it's even possible. I think this is one of those pieces that gets glossed over a lot. So how do GEBs actually work? So GEBs are capable of processing information from two primary places. So there's the information that's handled inside the building, and that's occupancy, temperature, CO2 sensors, and then just the statuses of all of the mechanical and electrical equipment that are in the building. And they're also processing external signals. It can be something as simple as what's the weather outside so that you can run your AC or your heating properly, to electrical grid emissions data and pricing data so that you can be most impactful for the grid for stability purposes. A truly grid interactive building is also actually providing the status of some of its energy usage back to the grid in real time. And that's why this deployment of, if you've ever heard the term AMI or advanced metering infrastructure, is really important, because you can't monitor what you're not actually, you can't control what you can't actually monitor and see. So in order for a building to monitor and then subsequently control their energy consumption, you need the brain of the building to be connected to each of these important components. That brain is called a lot of different things. It's called a BMS, or a building management system. It's also called an EMIS or BAS or SCADA systems. Once again, there's not a great governing body there, but they all refer to the same thing, which is an intelligent system that enables the monitoring and the controlling of a building. What they're doing is they're linking all of those individual pieces of building equipment so that they operate as one integrated system. And by having these systems, it's been shown to have savings of up to 8% of your building's energy consumption just by being able to monitor and control. Kevin, I'll just flag, I saw something pop up in the chat that I didn't see, but if there's anything important, feel free to pop in and stop me. So what is the point of having a highly controllable building? And in such, why is it actually important to have these in the energy transition that we're going through in the US? So this is a very traditional electrical grid load shape in much of the country. This one specifically is in an area called PJM, which is a independent service operator that exists in the US. And what you'll see is that there's peaks and valleys throughout the day when consumption goes up and down. The summer is often the highest load, which is when there's air conditioners running, which is a very big draw of electricity. And then those shoulder seasons are the lowest when the temperatures are at their least extreme. I'll note that there are some folks who believe that winter peaks may become as high or greater than the summer as electrification becomes a really big component. But if it's deployed strategically and in tandem with efficiency upgrades, these grid interactive efficient buildings can actually load manage better and actually prevent some of this additional winter peaking. So throughout the day, there's different generation resources that are dispatched to the electrical grid. And in that way, they're always making sure that the supply of electricity on the grid is meeting the demand. As more load is required, there's different resources that clear the market and are usually, not always, but usually more expensive and often have higher levels of carbon emissions. So throughout the day, there are different power plants that are meeting the electrical load. That can be anything from really dirty coal to really clean wind or solar, and anywhere in between. One really great shift that's occurring right now, though, is that renewables are being deployed as new sources of power throughout the US and increasingly throughout the world at a much faster rate than more carbon intensive resources. So this is driven in part by these renewable portfolio standards or voluntary targets that are being set by federal, state, city level governments, as well as individual utilities, which are setting targets for what percentage of power that they're responsible for generating or consuming must be renewable. Most of these targets are set to be fully renewable by 2050 or before, and the number of those states is growing every year. Now, unfortunately, that's a bit of a double-edged sword, which is what people are starting to realize, is that as renewable energy is added to the grid, that load curve starts to change and become less predictable. Renewable energy resources by nature are variable, resulting in less predictable or more dramatic swings in the availability of power throughout the day. So a really good example of that is this duck curve. As you can see, I did not draw this beautiful drawing, but it's become really prominent in areas like California that have extreme solar saturation. And what that means is that unfortunately, one of the big downfalls with solar is that we can't produce it at night. Surprise, surprise. That's also aligns pretty perfectly with when the highest level of demand hits the electrical grid, which is around 6 p.m. as folks return home from work and they start their air conditioners and they run their dishwashers. That's occurring at the same time that the availability of solar starts to wane for most of the year. The beauty of GEBs is that we can start to use them as a tool to combat this. So if done properly, what we can do with GEBs is that we can get these buildings to shift their loads en masse to better smooth out that load during the day. So if buildings are incentivized to do so, some of these technologies that I spoke about before can help align your building's consumption of electricity with the availability of those variable renewables. In this case, it's solar. It's moving your consumption of power into the middle part of the day when solar is actually available. So with that, I'll talk a little bit about what some of the value of these grid interactive efficient buildings are and what they can do for some of the customers and the grid operators. First and foremost, GEBs can provide savings to customers by avoiding peak demand charges and taking advantage of some of these time of use rates that are popping up across the country. Utilities can save on grid operational capacity and transmission and distribution costs. They can also help, like I was saying before, better utilize some of these renewable resources by shifting that consumption to take advantage of when the sun is shining and the wind is blowing rather than the parts of the day when they're not and you would need coal or some of these peaking power plants that I'll talk about here in a bit. But GEBs, with part of that stabilization and smoothing out of the electrical load, they're providing a more stable and resilient grid that's preventing dangerous blackouts that have started to occur in more frequency across the country. It's also really important to highlight that GEBs are capable of enabling a more equitable future. This is something that we've at RMI started to focus on, is that as we shift to the future, we need to look at stabilizing some of the cultural differences that are happening across the country. And part of that value of GEBs is that you can support these disadvantaged communities. What they are capable of doing is decreasing peaker plant emissions by minimizing the consumption of electricity during these dirty generating hours of the day, as peaker plants are often sited in low to moderate income communities. You can provide this greater resilience, which means less death and injuries from blackouts during extreme weather events, which disproportionately affect those communities. And these decreasing electricity costs that will happen are lowering the energy burden for folks who spend a disproportionate amount of their income on those energy bills. So grid interactive efficient buildings can use their ability to shift and shed demand to reduce carbon emissions throughout all the different stages of the grid transitions. So in different places across the country, as seen here, there's a different amount of renewable resources that are available. And as more of these renewable resources come online, that differential between clean hours of the day and dirty hours of the day becomes really dramatic. You can see places like what's noted on the slide here, IESO, which is Ontario's grid, which is predominantly hydro, predominantly nuclear. The differential between that and the peaking and dirty coal plants is very dramatic, and you can use that differential to apply when buildings should be consuming load. So if you can properly incentivize folks to charge their cars or run their dishwashers during the times of the day when wind power or hydro is providing electricity rather than coal, you can see pretty drastic reductions in emissions. So our team's research has shown that as variable renewable adoption becomes dominant, the potential for carbon reductions by utilizing GEBs could be as high as 40% compared to baseline consumption of power emissions. So beyond talking exclusively about carbon, in one of our other reports, we found that demand flexibility could actually cut a building's peak demand by 30 to 50% during specific hours, which as a building owner is pretty terrific. What it would do is it enables these owners to avoid high demand charges, which can account for up to 60% of their electricity bill. However, arguably more importantly, from a selfless societal aspect, GEBs are able to take advantage of granular marginal emission signals to determine when to shift their loads. And if they do so, you can consume it during less carbon intensive times of the day. And if enough people in the building stock do that, coincident peaks, which is when everybody on the grid is consuming power at the exact same time of the day, can be limited and reduces or eliminates the need for these really expensive and dirty peaking power plants. Those power plants really only run when the grid is the most stressed out, and they're disproportionately expensive. For example, they cost New York City residents 1,300% more than other resources of power. And they're also just inherently dangerous for society. They contribute a lot of localized pollutants to the air, like SOx and NOx, more than just CO2. So all of these things combined is you can have individual societal benefits to building owners who are doing this, as well as, individual benefits, as well as societal benefits. A really great example of the success of calling on GEBs to do this is during California's, they have something called a flex alert system. And that system was set up to help avoid grid failure over the last few summers in California. It's essentially California grid operators are sending out a request and saying, hey, if you can you shut off and conserve some of your energy for the next couple of hours? And it's had pretty sizable success. And that's even with the fact that it's completely voluntary. People are doing this out of the goodness of their heart because they want their power system stay online for everybody else. So the fact that that was so significant and impressive without incentives means that as we do incentivize better, we'll likely be able to be even more successful. So the last thing I want to talk about is how do we actually incentivize these better? Like I said, for the most part, people typically do not act without a reason, and having those reasons is really important moving forward. So why are you going to get people to turn their traditional building into a GEB? Well, the first of those is there's something that they're called demand side programs, like demand response, that have already been used across the country. And really only grid interactive efficient buildings can profit from them. So as a participant in these programs, a GEB would act as a resource option for these balancing of supply and demand for these authorities. And they're paid and they're kept on retainer so that when they're called upon, they can limit the amount of load on the grid for a certain amount of time. Utilities can avoid dispatching some of these more expensive power plants, and in turn, that leads to lower retail rates. It leads to less polluting resources on the grid. And as the number of distributed energy resources, or DERs, increases, and the potential for these GEBs to actually respond in time has improved over the years, these programs have actually begun to evolve. So you can see on the slide that we've moved away from some of these simple manual controlled demand response events into more sophisticated programs that provide even better services to the grid and more profit options for building owners to take advantage of. Another piece that we can do to incentivize investment in GEBs is that we need to make the prices more responsive and actually incentivize some of these buildings to consume power during the times of the day when there are carbon-free resources. So the most traditional of retail rates for electricity are based on purely just the amount of energy you consume in kWh and the demand. So the highest amount of energy you consume here, you can see like the tipping of these on this chart here, which is kW. And those are the charges that go to the customers, perhaps with a little bit of seasonal changes or chunks of time that have different rates. But as free market advocates at RMI, we believe that frequently updating prices, which tie some of these emissions intensities to the price, would be the most efficient way to incentivize some of these reductions. So you make people pay more to charge their car when coal is the only thing that's on the grid. The other way that you can incentivize GEBs, if we just talked about some of the carrots, is a stick. There's a pretty groundbreaking law that's based out of New York City that's called Local Law 97, in which you are penalizing building owners of a certain size, these are not single family homes, if they don't reduce some of their operational emissions. There's something in the pipeline here that's called the alternative compliance pathway in this law. And if it was implemented, it would require grid interactive efficient building owners to monitor emissions conditions of the grid and to limit their consumption accordingly, or else they'd be penalized for consuming when the grid is most dirty. So these are really new and interesting ways of trying to get GEBs to be moved onto the grid. And I hope they're all successful, because I want GEBs to be pretty prolific throughout the country and the world eventually. That is the end of my presentation. So thanks for your time.
Thank you so much, Connor. I just wanted to note in the group here that if you have any questions, please feel free to put it into the chat on the Zoom chat, and we'll respond to those at the Q&A session. So for our next speaker, we have Alicia, and she is with EDO, a new startup with their focus in Spokane, Washington. I just wanted to briefly introduce Alicia here, that Alicia has a background in planning that allows her to bring a systems thinking lens to decarbonizing our built environment. She has worked on business model innovation and program development in the energy efficiency and grid infrastructure spaces at Spark Fund, RMI, and the MIT Energy Initiative. Alicia most recently ran a nationally recognized smart buildings program for NYSERDA. She is currently learning how to navigate the many water bodies of Washington State. So I thank you, Alicia, for being here, and I will let you proceed.
Yeah, thank you, Kevin, and nice to meet everyone, and thanks to the EIN network for having us. As Kevin was saying, I'm Alicia Noriega. I'm currently Director of Projects on our R&D team at Edo Energy, and let me figure out how to pull up my slides here. 1 second. Okay. Should be able to see slides, right?
Not yet.
Interesting.
Perfect, it's on.
Great. Okay. Yeah, so thanks again to Kevin and the Energy Innovation Network. I think it's obviously a super relevant topic to EDO. EDO is actually based in Seattle, Washington, and is active nationally, but the Connected Communities program with the Department of Energy is based in Spokane, Washington, and I'll be talking about that after I give a little bit of an introduction to EDO as a company and what we do and kind of what motivates us to be in this space. So I always like to kind of ground us in why we're motivated to be working on grid interactive buildings in the first place. I think it's really easy to get into the weeds of things like building automation systems and Internet of Things, network architecture, and kind of lose why we're here, right, in the first place, like what motivated us to be working on these problems. And it goes back to kind of what Connor was talking about the amount of emissions that come from our built environment currently. It's 40% of global carbon emissions, and 3/4 of that is from the energy used within buildings, right? And looking forward, we're only going to double the built environment over the next 40 years, as well as preserve buildings that are, 80 plus years old and aren't really contributing to supporting our clean energy transition. So at EDO, we view, first of all, these three interlinked and interdependent crises: the climate crisis, the affordability crisis, and the equity crisis, as kind of key things that motivate us to work on demand flexibility in the built environment as kind of a key piece to creating a healthy built environment that is accessible to everyone, right? And maybe a little bit more about the linkage there. Smart grids and demand flexibility will reduce the need for new grid capacity, right? And importantly, free that investment that we would have otherwise made in building up the grid to cover, right, the peakiest of peaks, right? And build it more expensively and much larger than it needs to be. We can divert that investment with these innovations to be directed towards critical needs of energy burden customers, things like weatherization projects and electrifying transportation and building heating, which cause a lot of local pollutants, right, in low to moderate income communities first. So demand flexibility, I think, and its related innovations are just a really critical piece on delivering on these crises, right? Not to mention that a smart grid with grid responsive buildings, as Connor was saying, provides a more resilient power source, right, for all of the grid consumers. So that's kind of why we're here from a values perspective. I think a little bit about how EDO came about as a company before we dive into the Connected Communities program we're working on. This image I have up is an image of our South Landing Eco District, which is out in Spokane, Washington, in Eastern Washington. And this was actually a joint development between McKinstry, which is an engineering and construction firm here in Seattle, and Avista Utility, which is the utility that serves Spokane. And they had collaborated to build this eco district on a site that had been originally allocated as a substation. So they instead decided to collaborate on this non-wires alternative demonstration project, right, to show how an example of how we could have a development that serves has benefits for future occupants, right, the developers, the surrounding community, as well as provides the grid that amount of 1 to 2 megawatt export that it needed, right, to cover capacity constraints. So EDO was kind of formed in part to manage the operations and optimization of these buildings, right? So we got IP and have been developing energy management technology that specifically focuses on jointly optimizing buildings for occupant needs as well as, right, grid services. And just a little bit of a deeper dive into what's going on in this particular development. This is almost our living laboratory, which gives us a pretty unique opportunity to test various demand flexibility strategies and technologies, and to understand some of the value stacking between several different technologies. So How do they complement each other, right? What do we incrementally add maybe to other projects that aren't, as complex and don't look like this? What gives us the biggest bump in terms of flexibility? Excuse me. What gives us the biggest bump in terms of efficiency? Right, and understand more, and kind of test and experiment what we should be adding to more standard buildings, almost like a prioritized menu of options. So this has been an amazing living laboratory to kind of experiment in, and some technologies to call out that we have found, particularly useful in this context are obviously storage, which is a combination here of battery storage, thermal storage tanks, and phase change storage tanks. Occupancy-driven ventilation systems, right? So, and with those, we're balancing efficiency and occupant comfort and safety, as well as conditioning the building based on which zones are occupied and which aren't at given times of the day. And I'd also call out, the networked lighting systems, which can provide pretty quick sources of flexibility without snapback. So those are all super interesting levers that we've been experimenting with for these incremental flexibility versus savings benefits. At the same time, this was a greenfield development. It was a huge project, and buildings aren't going to look like this, right, in 99% of cases. And the goal at EDO is really to scale this load flexibility, this demand flexibility paradigm. And so we can't assume that every building is going to look like this and that we can just go into an empty site and develop kind of the perfect grid interactive efficient building. So our commercial offering right now that we partner with utilities on looks a little bit more like something that would fit into an existing utility demand side management program. So in the commercial market, we partner with utilities to offer what's considered an operational energy efficiency program that leverages advanced data collection techniques, as well as energy management analytics, to kind of identify ongoing and near real-time energy savings opportunities and provide root cause-based resolution. And this is really, getting our utility partners to move beyond what's often a building efficiency program paradigm of these kind of equipment replacement, one-off equipment replacement and rebate programs, and move beyond that to a more data-based, more persistent solution that can also inform and lead to other interventions, one of them eventually being load flexibility services. So when we partner with utilities today, the primary focus, it's still definitely energy efficiency, but with this type of solution, which industry calls EMIS, Energy Management Information System, there are a lot more things you can do than just identify ECMs, especially when the program is offered by a utility, as opposed to a lot of disparate vendors, right? Because if the utility holds this data and is offering the service to the customer, they're able to kind of look at that data in aggregate, look at customer targeting opportunities, kind of maybe issue buildings across their service territory, have that stickier relationship with customers and build the trust, to eventually get to this load flexibility services. So we think starting with this type of solution also leads us to have a deployed way to understand which loads in a building, for example, are flexible at any given time, and eventually enable our more supervisory control aspects to allow them to shed or shift these loads in more of an automated demand response or demand flexibility capacity. So this is kind of our bridge to realizing grid interactive buildings at scale. However, on the right side, where we're talking about this automated demand shedding and shifting paradigm, we haven't seen a lot of utilities kind of get to that point yet. A lot of them are still kind of in the first few steps of this. And what we're really working with a utility partner on building out in the Connected Communities program, which I'm gonna switch to talking about now, is building out what does your demand flexibility offering look like how are we doing this, right, with distribution level asset optimization? And so that's been a really exciting piece of work that we're just now getting ready to begin. So the Connected Communities program came from a Department of Energy funding opportunity focused specifically on grid interactive buildings. And they were looking for ways in the market to scale and equitably deploy grid interactive building developments. So essentially proposals really had to focus not only on the technology aspects, right, of implementing demand flexibility in buildings, but also the more social and economic pieces of it. And to do a 5-second brag for EDO, we were one of 10 winners out of around 250 applicants. So feel very lucky and grateful to be working on this with DOE and our partners. And we do have a utility partner working with us on implementing our proposed program, which is going to provide, we think, hugely valuable insights on how to make this type of deployment a reality elsewhere in other service territories, which is really, at the end of the day, the goal of this funding. So we need to dive into what our proposal looked like. Our project actually centered around a specific substation in this utility service territory that experiences some periods of congestion and stress on its feeders, especially right during times of peak load, during times of extreme heat, which was an issue for the entire Pacific Northwest last summer with the heat dome event that I'm sure many of you had heard about. So this project is focused on establishing a targeted virtual power plant from buildings that are connected to the feeder segments in this specific area. And ultimately, this proposed VPP will be able to be scheduled, forecasted, and dispatched pretty automatically and seamlessly by the utility, when needed. And when not needed, the retrofits that we make and the assets we deploy will concurrently be able to provide ongoing value streams to the building owners that are hosting them and the surrounding community, even when not being leveraged for the substation capacity relief services. And that type of value stacking is a really important part of this proposal. And so something that I'll continue stressing throughout this discussion. Maybe one other thing to highlight here is when I say we're building a targeted virtual power plant, I just mean it's going to be geographically specific, which differentiates this from more of an aggregator approach, like you see in California and other markets, where depending on the building archetype that the aggregator works with, you get kind of a scatter shot of recruitment from across a service territory versus needing to focus on activating flexibility across specific feeders, that are interconnected with the substation we're working on, which requires being able to recruit and work with and activate sources of flexibility in really different building archetypes and building use cases. So it is going to span the gamut of, first of all, different types of neighborhoods, different customer classes, and there'll be residential, small, medium business, large commercial, all integrated into this solution set. So that will be a pretty interesting challenge that we'll be working on through the course of this project. And maybe quickly to go over some of the top bullets to what we are committed to on the right side here. As it says, it's an $11.5 million program in total, including a $6.5 million grant from DOE and cost share contribution from our partners. We've committed to unlocking 2.25 megawatts of demand flexibility from buildings augmented by what you consider more traditional DERs. So solar, EV chargers and batteries are kind of in the traditional DER bucket. We've also committed to implementing energy efficiency measures to save up to 900 megawatt hours per year as a 5-year program. And we've equated this based on the grid composition to emissions reductions of up to 650,000 pounds of carbon dioxide equivalent per year. And I think overall, one of the big goals of This program is to improve the resiliency of the grid in the face of spiking heat events, right? Spiking cold events, and just all of the kind of atmospheric anomalies that are coming with climate change and that we've seen in this area. I think one of the really interesting anecdotes that has just hugely supported why we're doing this project is that heat dome event I mentioned that affected many states in the Pacific Northwest region. Actually also took out this part of the grid. It was over 110 for multiple days in a row, right? And extremely congested and stressed infrastructure on the supply side, as well as more demand from new air conditioning connections than the grid had ever seen. And we did find out that at some points this particular substation we're working on needed 50 amps or about 1 to 2 megawatts of extra power during those days, which could have been provided by this type of solution. And so this is where we really start to relate this back to resiliency and equity. We know that brownouts and blackouts have the deepest impacts on the grid's most vulnerable customers, right? So this team really views improved resiliency as a matter of equity and environmental justice as well. Grab a drink here. I wanted to talk a little bit more, just because scalability is such a huge aspect here, about our proposed approach for connected communities. And I should mention, we have not officially kicked off yet, so this is still very much in planning and development, though we do expect to launch this month. But just keep in mind, this is our proposed approach for now. A large focus of the opportunity was to propose something to DOE that could be scalable, right, to other service territories, and even, within a large service territory like we're working in. We decided to explore scalability through packaging solutions that might apply across a bucket of building archetypes. So a high degree of customization, right, in our proposed or designed solution just wouldn't be tenable, right? It would be tenable if you had all the same building type, building age, level of sophistication, use case, et cetera. But because of this geographically targeted approach, we needed to be inclusive of multiple building types, right, use cases, ages, et cetera. So we took a high level look at the range of buildings that we might encounter in the service territory and propose a number of packages that would make sense for those building archetypes. So we expect to see a lot of single family residential, a lot of small, medium businesses, and a lot of, or a number of large commercial buildings as well. And, as part of this, we are going to be doing kind of a cluster analysis on the load profiles in this area and further segmenting these building archetypes into buckets so that we can start defining and refining these solution packages, right, directly from the outset based on what will be most scalable in the area. And you'll see kind of the numbers on the right side of the screen represent aspects of potential sources of building flexibility, as well as those, what I was calling traditional DERs that we could pull in combination to activate the maximum amount of both efficiency and flexibility in these kind of buckets of building types. So in commercial buildings, flexibility might come from rooftop units or built-up HVAC systems, connected lighting or smart plug loads. And we would operationalize this flexibility from connecting to an existing building automation system or energy management system, which exists in a lot of large commercial buildings and which we have as an integral part of the EDO offering if it doesn't. Whereas the load flexibility in residential buildings will largely be from connected thermostats, controlling air conditioners, controlling heat pumps or water heaters, or even controllable EV chargers, which we're also planning to bring in. So we're super excited about continuing to explore this approach in the early stages of the project. And to give you an idea of what those stages of the project might look like, I'm sure I don't know if you guys can see this top bar on the screen that I can, that's blocking some of the years, but the years are 2022 to 2026. So it's a 5-year program. Each year counts as a budget period, and we do have a much, more detailed scope per budget period, but just wanted to throw this up here to give you an idea of how much kind of planning and surveying and iteration has to go into this at the, in the early years. And then in the later years, there's just going to be a high level of engagement and, testing and measurement and verification to make sure that the solutions we come up with are working for customers. The incentive packages can make sense. And one of the things we're really excited about is working on an M&V approach that's more appropriate for demand flexibility type services than the traditional IPMVP approach might be. So this is all getting us to this goal of eventually being able to scale some of the outcomes. And talking about goals, EDO has a pretty long list of what we see as our goals and what success looks like from working on a program like this. And I think, worth pointing out, all of our partners, including DOE, have their own set of goals and objectives here. So not speaking for any of them, but these are EDO specific key objectives. And starting with measuring how much demand flexibility buildings can provide and proving that out in a real world environment versus a simulation, I think is a huge step up in kind of advancing this industry. At the end of the day, I think a lot of utilities at least have questions on how much flexibility is actually available in buildings versus how much has to come from something like battery energy storage, right? And for those that have been kind of researching this concept for years, this remains a fairly large question and is, equally important to potential utility partners of ours who want to understand if investing in demand flexibility programs really just means putting a battery in every building. So this kind of first bucket, right, including this point about understanding the trade-off between energy efficiency and demand flexibility are really key questions for us to understand and suss out over the course of this program. And of course, the goal will be to publish broadly on this and share the findings. I think a related question that falls out of that is surfacing the true economics of non-wires alternatives. And our hypothesis there is that you certainly provide a lot more value and diversify your value streams by establishing these local DER solutions to support the transition to renewable energy versus doing it the old way of building everything over capacity and socializing that cost to ratepayers. But we intend to kind of fully document and prove that out over the course of this program. And then number 2 here, demonstrating our communications platform that optimizes demand flexibility dispatch. This essentially is talking about, we believe that to make this a true demand flexibility solution, which includes capacity and balancing services to utilities, among others, we need to be able to call on these load shed or shift resources quickly in an automated fashion, right? Not this form of demand response of the old days where you're calling up on the phone, your paper plan and asking them to turn everything off, right? This needs to be quick and it needs to be able to be called repeatedly throughout maybe the week or day and almost be unnoticed, right, by occupants of the building. So that type of grid optimization technology to do that all in an automated way in concert with what's happening on an overall distribution grid is still pretty nascent, and one of the things we'll be working hard to build out on the Connected Communities program. And then the last one here, obviously motivating customers to participate in these programs is one of the largest components of this and has a big equity component as well, right? How do we make these smart building platforms accessible, right, cost effective, and not create a situation in which it costs a ton of money to enter, a real-time pricing market or something like that if it did become available. So those are really thorny things to think through and deliver on. And luckily, we are working with groups that are familiar with the Spokane community and are definitely looking to bring in community organizations and other professionals in this space to consult on this really important part of the program design. So that is my presentation, and happy to answer any questions on any of that. I know it was a lot in a short amount of time. Thank you.
That was wonderful. Thank you so much, Alicia. And I saw there's some questions, and we will pose that in the Q&A session. So thank you. For our third speaker, we have Tochi, who is a senior associate energy modeling team lead at Mazzetti and an expert in the energy analysis practice. He has significantly expanded the firm's analytical capability through the development of new tools and processes. As a licensed engineer, he has a comprehensive knowledge of the complex building system optimization, HVAC controls, and system selections. I would like to put the floor to Tochi, and who will speak more about the vantage point from an engineering perspective.
Yeah, thanks, Kevin, for the introduction. Hi, my name is Tochi. Good morning or good afternoon, depends on, or good evening, depends on where you are. Let me share my screen and try to pull up my slides. Can you see my slides?
Yes, that's coming out clearly. Thank you.
Okay. I think it's also doing auto translation, so let me turn that off. Okay, great. I think thanks Corner and Alicia to lay out some of the background of great efficient interactive efficient building. Kind of what is GEB and why we're doing that and how we're doing that. So today I'm going to be just focusing on as a building design engineer, how we are approaching GEB to make sure that the building is great interactive and efficient. So, I mean, the content I'll be covering today is just the first one that would be just share of my some of my observations working in this industry. How the industry kind of like the design industry has evolved to this point that people start to talk about like the GEB. And then secondly, I would like just to introduce 6 metrics that helps the design engineer to evaluate GEB. And then the last but not least, I would like to touch on some of the design strategies we typically evaluate and implement into the design to enable GEB. So the first part, so I have been working in this industry for about like 10 years, and I feel like I'm lucky enough to witness the biggest revolution that is happening in this industry in terms of how we evaluate different design strategy and how different design strategy has been kind of implement into the design to achieve sort of the building decarbonization goal that we have set. 10 years ago, like nobody is really talking about GEB, like nobody has really defined what a GEB building is, or even thinking about like a building electrification, right? Because at that time, like natural gas is so cheap, and and the people hasn't realized the importance of building electrification to achieve some of the climate goal we have to kind of definitely meet. So. But nowadays, for example, like building electrification is certainly a trend, and in some local jurisdiction, it's become a mandatory requirement. So you have to design an all-electric building, right? So and then the promise of building electrification, for example, is really to the promise that the grid is going to get cleaner and cleaner. However, when we add more loads to the grid and we have so many kind of distributed energy resources at the demand side, which is in our case is the building side. For the grid, it becomes harder and harder for the grid to manage that, right? So as Corner pointed out in one of his slides, the duck curve is really the problem that we're facing nowadays when the sun goes down, all the renewable like we don't have any PV available, then you're going to see a peak kind of surge demand, typically like around 7 p.m., 6 p.m. to like 9 p.m. And so that's definitely some issue we have to deal with. And then I feel like, as a design engineer, we really, I feel like it's kind of our responsibility, even at the design and planning stage, to figure out a way to design our building and our on-site renewable energy to be more grid friendly. I think that's the only way that we can achieve an overall low carbon emission society. So next one, I would like just to touch on the 6 metric we usually use to evaluate a certain design to enable GEB. And then this metric was sort of came up with by a joint effort by NBI and US GBC. NBI is New Building Institute, is also a nonprofit organization focusing on new building technology. And the US GBC is kind of the party who holds the lead, which is the green building benchmarking system. So they came up with this metric for the design engineer to use. So the first one, the grid peak contribution, is really a metric to help evaluate the your building peak demand, or building demand contribute to the grid peak demand, right? So, and the goal that you want to achieve is that you want to avoid your building peak demand that coincident with your grid peak demand. You want to kind of lower that as much as possible. That's kind of a load shedding or the load shifting strategy you can use to achieve that. And then the second metric is grid carbon alignment. You might also kind of already aware of that, like the grid peak demand and grid carbon emission is actually doesn't align with each other just because of the renewable energy penetration on the grid. So the second one is really similar to the first one, but is really trying to avoid that. When the grid carbon emission is highest, you want to make sure that your building load is kind of as low as possible, and you want to shift the load to the period when the grid carbon emission is the lowest. So that's sort of the goal of the second metric. And then the third one is the site renewable utilization efficiency, is basically to evaluate how much renewable energy you can consume on site, so you don't have to push it back to the grid, because the grid has already a lot of work to do. And then the fourth and fifth is quite similar. The short-term demand flexibility, long-term demand flexibility is really the short term is really to evaluate how much of a building demand you can reduce for an hour. That's short term, and the long term is 4 hours. So again, how you can achieve that is by maybe having a on-site battery system, or enrolling a demand response program that can really kind of lower your demand during those periods. And then the last one, the dispatchable flexibility, is kind of a similar fashion to the fourth and fifth, but it is more like talking about the automatic demand shedding capability, which is basically kind of you receive a signal from the utility. Like this is when the grid is getting the peak. Now you have to kind of shedding your building load. So that's kind of what the last one, dispatchable flexibility, is evaluating. So I'm going to go through each one of them pretty quickly. So on the grid peak contribution, in order for us to evaluate or trying to avoid your building peak coincident with your grid peak, you have to understand what the grid peak demand really looks like. So what we're seeing, this heat map, is basically representing what the grid peak demand really looks like. So on this heat map, the x-axis representing the 12 month, from January to December, and then the y-axis is really about like 24 hours. And then the green piece basically means low demand, and then the red means high demand. And you may notice from the note below that I actually intentionally choose this data set, which is actually a projected future demand on a California grid for a year of 2036 to 2044. Just to demonstrate how reachful data that we have available nowadays compared to, like I said, like 10 years ago. So we have like significant amount of data set that we can utilize to help our design practice. again, this data set was, in case you are interested in it, this data set was published by Unreal and called the Cambrium data set. So they're basically doing a bunch of like simulation, evaluating different kind of a policy out there, trying to project what the future grid demand is gonna look like. Again, we have, so nowadays we can not only kind of simulate or evaluate the current like grid demand, we can also, look at what happens in the future, because that's important for at your design stage. You not only focus on today, you also should be focused on the future. So from this heat map, basically it's kind of intuitive, right? So you're going to experience the peak, the grid is going to experience the peak demand in summer, late afternoon from 3 p.m. to maybe 7 p.m. So that is kind of driven by the space cooling usage for all the demand side, right? And then at nighttime, it's kind of experiencing a low demand because all the activity basically can kind of shut down. So that's what the grid demand looks like in the future. And then the similar pattern is going to stays with the current demand, with the current grid demand. So the second one, the grid carbon alignment, is similarly, in order for us to evaluate the grid carbon alignment, you have to know what the grid carbon emission looks like. And again, I'm using the same data sets, like I said, the future projection of the carbon emission on a California grid. And this is what it looks like. The heat map layout is very similar, but here you can see like really the grid emission is really low in the spring season during the daytime. That is just because we have abundant PV available on the grid, and even like in the summertime, it's not that high compared to the peak demand. So understanding the difference between this and then how do you optimize both the demand side and the carbon emission is very critical for you to kind of design a certain feature or trying to optimize your control sequence of your building operation. And then on the carbon side, basically you peak carbon emission really happens at night when there is basically no renewable. So the grid is basically powered majority by natural gas power plant. So that's where they're seeing is peak in winter time and nighttime, winter and nighttime. So again, this is all sort of the future projection. I also have a graph kind of just showing what it looks like currently. It's actually 2 years ago, but I think it is still a good representation on what's happening in the California grid today. So on the left side is basically illustrating throughout the day, which happens to be September the 24th, where the energy actually comes from. And if you can just focus on the green line, for example, like this is when we have some kinds of like the renewable energy, which is mainly like solar. When the sun comes up, you can see, majority of the power is going to be served by the renewable. And then when the sun goes down, there's a big drop on the renewable energy sector. So that's why, natural gas power plant has to kind of pick up that load. That's essentially what the duck curve really is about, as Connor mentioned in his slides. And then on the right hand side is basically carbon emission, like the real-time carbon emissions throughout the day, the same day. As you can see, we are really experiencing a ramp up in the late afternoon. So that's all the data we have available. Like I said, by using this type of data, we can at the design stage evaluate like a different design strategies to make sure that the building, when it is being built, it kind of already kind of incorporate those features that enable the gap. So this is on the grid side. On the building side, I also want to show a few examples, also kind of basically demonstrate, like, depends on the building typology, depends on the climate you are in, you're gonna probably see a totally different like a building load profile. So the energy efficiency measure or the design measures that enable the gap are gonna be totally different or significantly different. So for example, this would be a typical office building electrical load profile in the Bay Area looks like. Again, if you see that vertical strip, that's basically representing the weekday versus weekend. Apparently, you're gonna experiencing higher load during the weekdays and the lower load in the weekend, just because typically the office is gonna shut down in the weekend, and then you're definitely going to experiencing, the peak demand happening in the summer, during the daytime, and a little bit in the afternoon, primarily driven by the air conditioning load, and then the at nighttime you barely see any. I mean, the load is really sort of small, that base load. So on the contrary, if you look at the multifamily high-rise residential building in the Bay Area, this is what the electric load profile going to be looking like. I mean, it's basically very kind of a reverse of what the commercial building would look like. The electrical load for the residential building is going to really lowest during the daytime, because you're assuming that nobody going to be in the apartment, people go to work, and then you're really kind of experiencing those peak time or peak demand around 6 p.m. to 7 p.m. in a summer season, right? So when people get home, they start cooking, turn on their appliance, right? So this is a totally different kind of demand pattern than the commercial building. So how you can kind of alleviate the pressure on the grid, for example, for the residential, I mean, you wouldn't kind of shift your dinner time, right? That's impossible, but you can definitely, shift your maybe dishwasher or, washer or dryer, operating time to a lower, in the late evening or kind of in the morning, to avoid the peak demand that going to be coincident with the grid demand. If you remember what the grid demand looks like, this is exactly coincident with the grid peak demand. And on the air conditioning side, you can essentially doing some load shedding. There are like the Nest thermostat or out there that could automatically respond to a signal that reset the HVAC system, set up at temperature to basically kind of reduce the peak demand. So that's another kind of strategy that you could do to avoid those coincident happening. So that's the demand and the carbon kind of alignment. The third one would be the site renewable utility efficiency. So the graph that I'm showing in here is kind of a real project electrical demand versus a PV generation on site. As you notice that actually we in this particular project, we actually generate excessive energy than the building requires throughout the day. So basically, to get a higher score for the site renewable utilization efficiency, you have to kind of install some on-site battery to store the abandoned electricity generated and to be used for a later time. And then, just one example kind of showing the what we typically do in terms of at the design stage, trying to optimize your PV system and the battery system to reduce both the peak demand and carbon emission. So what you're looking at in this graph, I just kind of use a day as an example. So if you look at this light yellow line, that's without any renewable energy, any control strategy, what the building load looks like. And then the gray line is what the actual demand the grid is seeing. So as you can see, like you really intentionally kind of reduce the demand, or you reduce the load that the grid is seeing during the kind of late afternoon time, which is from 5 p.m. to 8 p.m. and shift those loads to the early morning when both the demand and the carbon emission is the lowest on the grid. So that's kind of a control that you can implement into your spec and integrate into a BMS system, the building automation system. So on the PV side, the green line representing the PV generation. So it's not significant, in this particular project. It's way lower than what the actual demand, the building demand you have is. So you're gonna just use them all, like whenever it's available. So the battery gonna take a kind of a very important role to make this happen. So basically, you are actually using the grid to charge your on-site battery in the morning, and then store it to be used in the late afternoon. So again, like I said, this is a really way to alleviate the load pressure on the grid to the better time. So that is what we could do in the early design stage, like how we planning the building, how the building can integrate with on-site renewable energy to better kind of enable gap. So on from the fourth and to the sixth, which is all talking about demand flexibility, I would like to talk about like as a whole. Again, like I said, it's very similar fashion. You can say it's really talking about the load shedding capability that you have. So the short term and long term, again, like I said, is looking at the 1 hour load shedding. Long term is 4 hour. Dispatchable is more kind of automated, receiving a signal automatically, kind of reset your building demand. Again, some of the requirements is also embedded in the code. So for people who don't know, like Title 24, which is the California Building Energy Code, that actually specify the requirements for demand response program. Again, right now, it doesn't mandate the building has to enroll in a demand response program, but they're basically saying your BMS system or the building automation system has to be demand response control ready, which basically means that all the infrastructure has to be there in order for you to use in the future. So in terms of the demand responsible control, all the BMS system has to be open ADR, which is open protocol developed by LBNL, Lawrence Berkeley National Lab, which is kind of open protocol that enable the communication between the utility signal into your BMS system. And then it has to be communicated using different protocol like a Wi-Fi backnet. And then when we actually got to the demand response program, what really means at the building level, it could mean, on the HVAC system, relax your heating and cooling set point about 4 degrees in the, non-critical zones. So for example, like healthcare hospital, you probably don't want to have this because it's very critical to have kind of maintain a more stringent thermal environment. For the lighting system, you basically it requires that the building should demonstrate a lighting power reduction to a 15% reduction compared to design level. And then I haven't dealt with the electrical message central control that much, but basically, it requires that it has to be 30% lower than your design value. So those are the code language already in the requirements. So kind of reinforce on the building industry to incorporate demand flexibility. So again, the last but not least, I would like to touch some of the design strategy that we typically evaluate to enable gap. Again, I also saw corner slides also have this DOE gap roadmap graph, which is, you always want to start with efficiency, right? So instead of shedding or shifting, and that's always something that you should, look at the first, right? Trying to reduce your demand. And then some of the measures we typically evaluate to enable energy efficiency building would be like starting with the building massing and orientation, should be designed for solar access and could be integrated with passive heating or energy generation system. The massing orientation, facade design, high performance building envelope, high efficient lighting system, high efficient plug load, and energy star labeled, natural ventilation, which is passive design strategy, heat recovery as much as possible, both including air side heat recovery, but also the water side heat recovery, high performance HVAC system design, like a decoupled system, reading system, on and on. Those are the measure you definitely we would look at to enable energy efficient building. And then after that, the load shifting, which is this graph representing, shift the load in the late afternoon, maybe to an early morning or even at night when the demand is lower, where you can think about, natural ventilation again, plus net flush, right? Kind of charging your concrete slab to store some of the cooling. So during the daytime, you don't need that cooling that much. Thermal storage wall, reading slab, system pre-charging, thermal energy storage tank. Again, this kind of the thermal storage. If you think about it, it's essentially a thermal battery, kind of shifting the load from a peak to non-peak period. And then after that, load shedding is talking about like it's more, in my opinion, like more in the operational mode that you can receive a signal from the utility that can shed the load. But in terms of the electrical load shifting, that's where the battery or even like hydrogen fuel cell gonna come into play. like I think hydrogen is definitely in the horizon. I think at this point it's definitely not economic at the building level, but it certainly should get more attention at the utility scale and on the transportation sector as well. So those are the things that I think if there's a breakthrough, we should definitely look at the building level. And then in terms of the shedding, like I mentioned, the demand response, reducing your lead level, temperature setback, delay your water heating, those are the things we typically kind of look at to enable GAP. Lastly, that is all what's gonna be required at the design stage. In the end, it has to come into the operation, which both Connor and Alicia has talked extensively in terms of in operation. How do we enable a GAP? So, and I think in my opinion, it's definitely come from a multidisciplinary effort. The cloud computing technology advancement, the AI big data analytical side, the LT sensor, the advanced control technology has been involved. Open protocol, like I said, the open ADR, which is the demand response, open protocol, and also kind of the renewable energy development. Now the PV become much cheaper than it used to be. Battery is still kind of cost prohibitive in some of the building, but I definitely have the faith that it's going to get better and better, more economic. So all those kind of different multidisciplinary environment are gonna, I think in the end, definitely helps the involvement of a grid integrated building. So with that being said, that's all I want to share. Thanks for listening.
Thank you so much, Chita. I really appreciate you going through that. Right now we are at 10:30 a.m. I would like to open this up to our audience. We have about 15 minutes for Q&A. I saw that there were some questions in the chat, so I was hoping we could initiate those items.
I can take one of the ones from James that came through.
Great.
James had asked, since it involves a significant amount of technology to implement GEBs, how we're going to harden against nefarious actors and cyber attacks. It's a really good point. As more and more items are connected, that means more elements of your building can be at risk. And there's one element of risk of somebody turning off your dryer, but there's a much bigger element of somebody taking down a data center or taking down some of the elements of the electrical grid that can be affected in mass. But these people who are doing some of the design considerations on buildings. So I had previously worked as a controls engineer, so I can speak a little bit about that. Is we think about it constantly. There are different elements. I'm not a cybersecurity expert, so I can't say specifically, but a lot of our components are designed with end-to-end encryption. And when it's necessary and they're mission critical components, we often do something called air gapping, where we will install our systems that control the mission critical components of the large electrical equipment, or things that you have higher concerns of security are on a completely isolated network with only a single point of entry within your network to be able to be accessed. So you're minimizing the exposure to public networks through smaller single entry points. That way you're minimizing the exposure to the larger part of the internet.
Thank you so much, Connor, on that. Are there any other questions from the audience? And feel free to ping here. I can.
And Kevin, I actually got disconnected from the chat. So when I got bumped, so I can't see any of the questions. If you want to read one to me, I'm happy to take a stab at it.
Sure. There's a question here. Let's see here. There's a question regarding EV adoption. Are there plans to accelerate or incentivize vehicle to building applications as means of distributed energy storage? Any thoughts on how to offset battery degradation costs in such applications?
Yeah, I mean, that's a great one. I think vehicle to building is a huge area of interest for us at EDO. Right now, we're kind of able to take a charging profile and represent it on our dashboard that a building owner can see. But the question is, like, what do you do with that information, right? How can you kind of co-optimize that charging schedule with what's going on in your building? And I think it's an emerging area of research for many firms at this point. In terms of our work on connected communities, we are going the route of certainly optimizing charging while a vehicle is parked at a residence, which is much easier to get a customer to opt into, right, than having the vehicle be on like a smart charging schedule while it's driving around town or, you know, parked at an office, because there's a lot of range and charging anxiety of like when you're out and about, you want to be able to jump in your car and go. So we are kind of exploring different incentive models on how to enable that type of smart charging infrastructure and opt-in throughout the day, because when a vehicle is parked at home, it's usually overnight, which is arguably when a grid is perhaps least stressed, right? And maybe wouldn't be optimal to providing grid congestion relief services at that particular time. But super interesting question, definitely looking into it. And I see now that I'm like popped back, I can see the questions now. There's one by Rodney that I think is really interesting. Do you mind if I go for that one too, Kevin?
Sure. Did you want to read out the question for the group?
Yeah, Rodney asked, could panelists discuss pros and cons or concerns of demand flexibility directly controlled by the utility, so direct load control, and use of price signals that the owner or occupant can respond to or opt out of via a building management system or something similar? This is a big ongoing question for us at EDO. I think there's pros and cons to both. I think exposing customers to real-time pricing has always and will continue to have some equity concerns, right? Like the people that have the mechanism to respond to those pricing, right, would, maybe be more on the class A commercial office buildings versus folks in low to moderate income communities or folks renting, that sort of thing. So exposing all customers to real-time pricing is probably not the way to go. I think we lean more towards this concept of honestly direct optimization and control from the utility, obviously with options for customer opt-in or opt-out. And I think to another question that's on here about barriers, kind of, it relates back to customer trust in these solutions being implemented in their buildings and getting that user experience really tuned in so that individuals don't feel like their utility is kind of reaching into their home, right, and adjusting their thermostat. Making sure the experience is not only seamless, but if a customer does choose to participate in something like a demand flexibility market, that participation is adequately valued, right? It is a cost for them to participate, and it is a huge value to the utility to get a critical mass of customers willing to do something like a direct load control program. So just assigning adequate value to that as well, I think would be a huge barrier relief, I guess.
I think there's also an important element there where it doesn't necessarily have to be one or the other. You can have utilities which allow for different aggregating groups to interact with building owners or residential homeowners or whatnot, so that it's not maybe utility who is coming out to you and flipping some of your elements of power on or off. It's you have a third party who's offering a service and saying, would you like to co-optimize for cost or for comfort for certain times of the day? Do you want your EVs to be charged or your dryers to only be run when the grid is at lowest carbon emissions or lowest cost? So there are groups that can come in and sort of work as that intermediary who might be able to offer a better customer experience than the utilities could offer on their own.
Excellent. So it looks like there's not any more questions on the group chat. I will bring up some questions here that, excuse me, that I have prepared. So I wanted to ask to Alicia on what do you see as like the top 3 challenges for the connected community vision?
Yeah, I think one of them, I'll go back to that barrier I just outlined about making sure the customer experience is seamless, right? And there's not a feeling of kind of reaching into a building and controlling it or affecting the occupant experience in a negative way. I think when we're implementing automated demand flexibility solutions that are supposed to be automated and maybe responsive within an hour or even less time frame, we really have to ensure that seamless user experience, and sometimes gaining that trust with building owners and occupants can be a hurdle. And that certainly will be no different when we're recruiting participants for connected communities. I think another big one for me certainly is just the regulatory environment. I think that incentivizing the types of behavior and programs that we've been talking about this whole time and creating these demand flexibility markets really stems from being able to offer new types of business models and new types of incentives and rates where there maybe are where the utility is exploring maybe different asset ownership models or joint ownership of flexibility assets with their customers, or flexible or fixed rate pay schemes with kind of flexibility risk baked into a third party. There's a lot of different I think business models that are out there and great ideas around this, but we don't really have a sandbox regulatory environment for good reason in many areas, but there needs to be some happy medium where we are able to experiment and deploy more quickly with these kind of demand flexibility conducive concepts and models. And also obviously protect consumer interests and building owners, of course. So I really want to get to a regulatory environment where utilities are at least empowered and motivated to try these things out, right? Non-wires alternatives is a great example of this. It has to be valued and pushed from a regulatory level because otherwise this model of just building more infrastructure and rate basing that will continue to persist. And then I think another big hurdle for connected communities, which I also saw come up in the chat, is ideas around cybersecurity and nefarious actors, which are certainly, a huge focus area for us and what we're trying to do. And I think for everyone working in that larger IoT and networked architecture space, we do have a team dedicated to looking at this, and on connected communities, we have planned threat evaluation exercises, right? Both working with the utility and what they're worried about, and with some test customers. And we've taken a lot of cybersecurity measures with the gateway that we put in buildings and have kind of planned penetration tests regularly. So I think that assurance around cybersecurity is a barrier and one that we're working on as well. We can't hear you, Kevin, or I can't.
How about now? Okay, great. So just approaching here at 10:45, I do want to note that we do have a survey that we've put together, and that is in the group chat. We would greatly appreciate if you could take a few minutes to fill that out once we conclude. It would just help us inform us on how we did, and going forward, what topics and ways we can improve for future webinars. As we wrap this up, I do want to thank all three of our distinguished guests here, Connor, Alicia, and Tochi. You've done an amazing job introducing us to this new change in how buildings are going to become a resource, and considering the effects for the grid as our demands for electricity continue to increase. And with that said, if there's no other questions, I want to put that out there. I just want to give one more chance. Are there any other questions that the audience would like to put out? All right. Well, with that, then, I just want to say a big thank you.
Thanks for having us.
Thanks.
Excellent. All right. Wish everyone well, and have a good day and a good evening. Bye-bye.
Thanks, you too.